In this video, we'll discuss a few more examples on the fundamental theorem of calculus, part 2, right? So let's again here discuss what is part 2 quickly, and we'll see examples. So the fundamental theorem of calculus, part 2, make a nice connection between definite integral and antiderivative, right? Definite integral, which is a limit of some Riemann sum, very hard to evaluate. Antiderivative in the other side, in the other way, is a bit easier to evaluate if you know derivatives, right? So they are connected. That's why this result is called the fundamental theorem of calculus. We are starting from a very nice very strong assumption for a function. The function has to be smooth, has to be continuous. Sorry, smooth is way stronger. Has to be continuous, and then integration from a to b f of x dx is basically capital F of b minus capital F of a, right? What is capital F? Capital F is antiderivative of lowercase f, where f prime equal to f. So in this case, to evaluate some definite integral, you don't have to go through the long evaluation of very complicated limit at infinity. All you need to do is figure out the antiderivative of this function here, right? This current function f. Then you plug in b and plug in a, do a subtraction. So now let's go to our examples. We want to evaluate uh, integration from -2 to 1, x to -4 dx. So let me try to do the evaluation. You tell me that's correct or not, right? So we know that integration, we have a formula, right, for power function, antiderivative, right? So the antiderivative of x to n, as long as n is not -1, right? N here is different from -1, is x to n plus 1 over n plus 1. So this is the antiderivative is x to n plus 1. Oh, we know what is n here, which is -4, which is -3 over -3. Then plugging 1 and -1, 2, right? This is a notation representing you have a function, you have a straight line, then you plug in the upper bound into the function minus plug in the lower bound into the function, right? So this is equal to 1 to -3 over -3 minus -2 to -3 over -3, right? What's wrong here, right? This is not right. I can tell you this is not right. Why is incorrect? Because this will give you a negative number. This function here is always non-negative, right? To the power 4 is always non-negative. But this number here will give you a negative number. Why? Why is it wrong here? Okay, so now you can see that this calculation is wrong. Because what? Because uh, x to 4, -4, this function is not continuous on the interval from -2 to 1. In fact, f of 0 does not exist. right? So before you apply the fundamental theorem of calculus, you have to check the assumption. Otherwise, you get a number which doesn't make sense, right? So this is not this is very important before you apply uh, any result. You have to check whether the assumptions are satisfied, and then you can do that. And so then let's try to do some examples where the assumptions are satisfied, right? The function is continuous. So let's say this, and okay, so let's see this one. Integration from 1 to 18 and square root 3 over z dz, right? Let's try to figure out what's this. The variable here is z here, right? So we just want to use the collection of the antiderivative of elementary function. So this is integration from 1 to 18 square root 3 over square root z dz, right? Change your function to a standard form of elementary function, sine, cosine, secant square, or right, standard form. This is not a standard power function, right? So this is equal to integration from 1 to 18 square root 3 times z to 1/2. And 1/2 is not negative 1, right? We can apply our formula, and also negative 1/2. Also, on this domain from 1 to 11, z to negative 1/2 is always defined. So we can apply the fundamental theorem of calculus. So this is root 3 z to negative 1/2 plus 1 over negative 1/2 plus 1, right? Then plug in z equal to 1, plug in z equal to 18, and do a subtraction, right? So this is equal to root 3 times 2. This gives you 1/2, and flip it, get 2, times root 2, which is root z, right? Root z, which is plug in 18, you get root 18 minus plug in 1, you get 1, right? So this is how do we evaluate this definite integral, apply the fundamental theorem of calculus, right? This from here to here, we applied FTC part 2, right? Fundamental theorem of calculus part 2, right? So now let's see uh, one more example, right? Example 2 here. Example 2. Let's see this, right? So integration from 1 over root 3 to root 3, 8 over 1 plus x squared dx. Okay, so here we just look for the collection of the antiderivative formulas, right? Do we have a function whose derivative is somehow look like 1 over 1 plus x squared in the denominator, right? We do know that, right, check our memory, arctangent of x prime is 1 over 1 plus x squared. So arctangent is the antiderivative of 1 plus x squared, right? So what you do is, let's take a number, doesn't matter at all. If you take a differentiation or integration, you can take 8 out, integration from 1 over root 3, 1 over 1 plus x squared dx. Then you apply the fundamental theorem of calculus part 2. So this is h times arc tangent of x, then plug in square root 3, 1 over square root 3. So this is equal to h arc tangent of root 3 minus arc tangent of 1 over root 3. So that's basically how do we evaluate this definite integral. And yes.